Welcome to video instruction on the chain rule. To begin, let's go ahead and scroll down whoops, and take a look at the definition of the chain rule. And also to make the connection that this is a structure rule. Let me just start with that. This is a structure rule, which basically means it's not with respect to a specific function, but in general for all functions in the form of f of g of x, which is a composite or a composition of functions. So this is how you would take the derivative in this case. Okay, so starting out, let f and g be functions for all x in the domain of g for which g is differentiable at x, and f is differentiable at g of x, which ends up being its input value. The derivative of the composition, they're going to call it, in this formula here, they're going to call it h of x to give it one title, but it's the composition of f and g. So here's the normal notation, and here's like a Leibniz notation. I'm going to go ahead and elaborate on this a little and dissect it. So that's what's going on in this box. So what we're going to do is we're going to take the derivative with respect to x of f of g of x. And my d's don't look like d's, do they? Okay, so here's what it is. You're going to take the derivative of the outside function f, leaving g of x unchanged, chaining on with multiplication the derivative of the inside function g of x. So that's the notation. What I'm going to do is pause the video and I'm going to write in words, and I'll explain that in a minute. Okay, the reason I'm writing words with this is because if you learn the words, it basically will instruct you through the process or the structure. So what you're doing is you're taking the derivative of the outside function, leaving the inside function unchanged, times the derivative of the inside function. So we're going to kind of flow with those words as we work through these examples. So there's nothing else to really go over aside from just examples showing how to use this rule. So starting off, we're going to take the derivative of f of x, which you can see is a composition of two functions. It's good, and you don't have to write it down, but it's good to know what is your outside function. So I'm going to go ahead and list them for a few, and what is your inside function. And hopefully it's easy to see that there used to be an x in place of the x squared plus 3 for the outside function to be x to the 100th power. And therefore the inside function is x squared plus 3. So hopefully that's easy to see. So when we go through and we're taking the derivative of, we're going to denote f prime of x is equal to. So we're going to take the derivative of this outside function, and since it's a power function, we're going to bring that power 100 in front as a constant multiplier, times, and then I'm going to keep a big parenthesis here, big enough to fit this inside function, and then we're going to subtract 1 from the power, making it 99. So what you see currently is the derivative of the outside function, and I think I'll change the color and put the inside function as x squared plus 3 so you can see that easily. And then we're going to take the derivative of just the inside function. So there's two derivatives that go on. Derivative of the outside function, leaving space to rewrite the inside function exactly as you see it, then times, and if there's two terms, it's good practice to put parenthesis instead of a dot, the derivative of this, which is just going to be 2x. And then you can clean this up with algebra. 2 times 100, 200x, times x squared plus 3, that quantity raised to the 99th power. All right, there's your first chain rule example. All right, moving on. In this particular example, anytime you have a trig function raised to a power, it's probably a good idea to at least see it in your mind as the sine of x, the whole thing raised to the 5th, or even write it that way. And you should be able to identify the outside function, I'll just put O for outside function, would be x to the 5th power, and the inside function is the sine of x. So hopefully that's very clear. So when we go to take the derivative, g prime of x, it's going to equal the derivative of the outside function, which is 5, leaving space, and then that's the 4, subtracting the 1. You're going to go ahead and leave the inside function unchanged, and then chain on the derivative of that inside function, which is the cosine of x. Okay, so there's that. There's really not anything more that you can do algebraically. You can rearrange things if you want, but no need for that. Okay, moving down to example number 3. So in example number 3, I want to point something out. Do you see that you've got a big square root around 2 terms in here? So it's kind of, you know, you've got the outside function, which is the square root of x, and then you got 2 terms subtract, or 2, not terms, but functions subtracting inside. So a little bit of a combination of structure rule, which is normal. What I want to point out is that outside function, which is the square root of x, if we were to ahead of time think about its derivative, and I'm putting this here with a star. The star, if I write it down, means this is something I highly recommend that you memorize. And so you turn this into a fractional exponent first. Oh, that's a 1 up there. And then go ahead and apply the derivative. So dy dx would be, you're going to bring the 1/2 in front, and then it's going to be x to the 1/2 minus 1, which when you subtract 1 would make this a negative 1/2. And then when you pull that down into the denominator, it's going to be 1/2, turn it into a square root, it will be this. Now I highly recommend that when you memorize taking the derivative of the square root, because often it is an outside function. So let me explain. So now if we're going to go ahead and take the derivative, we're going to say dy, we'll just say dy dx, whoops, not dd dx. Okay, so dy dx is equal to derivative of that outside function, already have it memorized, is 1/2 times the square root, and then we're going to leave space for that whole inside function. So that right there, again, is the derivative of the outside function. We're going to just rewrite that inside function as it is, unchanged. And then we're going to go ahead and chain on its derivative. So the derivative of secant is maybe not something that you have memorized. You can look it up or work it out or memorize it, but it's chances are you better memorize it. All right, so anyhow, the derivative of the secant right here is secant times tangent. So I'm going to go ahead, since there's 2 terms, and put a parenthesis, and it's going to be secant of x times the tangent of x for that first, let me fix that first term. Okay, it is what it is. And then minus, if you notice here, this is e is an irrational number, and x, so this is actually a linear function. So when you take its derivative, it's just that slope. And so there you have it. You could go ahead and write that on top to make it prettier if you want. So maybe I can write it better. Secant of x, tangent of x minus e, all of that over 2 root secant of x minus e to the x. All right, so there's that derivative. Okay, now from here on out, I'm going to let you try these, but on this one, I'm going to give you a little bit of insight. It would be a very good decision to write this with that exponent, which is a 2 in the denominator, to pull that up and put it as the tangent of the quantity 3x squared. That whole quantity raised now to the negative 2 power. And you can see we've got a function within a function within a function. So you'll just keep chaining it on. And let's see how you handle that. I'm going to come back in a minute. Okay, so take a look. You can pause the video and take a look. But first place, we brought this up here. Here's the full derivative before we start to do any algebraic simplification. So after that, I went ahead and multiplied these, got this, and here's this up here, brought this down below. And you can possibly leave it like that. You're going to, in this course, be putting stuff into the computer, and you know, whether you might want to try and see if it recognizes, otherwise it might want you to simplify, which would be to turn this into 1 over cosine squared, this into sine cubed over cosine cubed, multiply by the reciprocal, cancel out your cosines, and then you'll end up with this. Okay, it's good to review your algebra, and so I recommend doing that. Okay, next one, looking at this, you notice that sine of x is your outside function, and your inside function is a quotient between these two. So what you're going to do is you're going to say dy dx is equal to, derivative of the outside function is going to be cosine, and you're going to go ahead and leave this unchanged, cosine of x, and then times the derivative using that quotient rule. So the quotient rule is going to take the derivative of the numerator, which is 2x, times cosine x left unchanged, minus, oh, I think I need a little more space. Shouldn't have probably put that in. Okay, and then minus where were we at? Okay, derivative of this left alone, times this left alone, times the derivative of cosine, which is the opposite of sine of x, so you might want to quantize that, over cosine squared. And then go ahead and clean that up a little. And basically cleaning it up is just probably turning that into positive. And so I'm just going to, here's what I can do is change this and then change that. How about that? There you go. Okay. All right, go ahead and try this all by yourself. Okay, so did you rewrite this cubed root to the power of 1/3? Hopefully you saw that. And then here's the derivative of that outside function. Notice that you've got a function within a function inside. So next you're going to take the derivative of tangent, which is secant squared, leaving sine of x unchanged. Then you're going to do one more chaining on of the derivative of the sine of x, which is cosine of x. So it's just continual chaining on until you deplete that. So now pulling that down into the denominator, making it into a radical. That should be that. Okay, one more example. And this example, it's asking you to find the equation of the line tangent to this at x equals 1. So again, you're going to need a point and you're going to need a slope. So find the value of the function. So you're looking for the point to evaluate f at 1, find the y value, and then find f prime and evaluate it at 1, and then fill it in. Okay, go ahead. Okay, so hopefully you got 1 when you filled the value of 1 into the function. When you took the derivative, hopefully you had this. We don't, if we're only using it to evaluate the slope at 1, you don't necessarily have to simplify. Fill in 1, do your arithmetic, you should have gotten 2. You can leave it in point slope form or change it to slope intercept form. And I'm not sure which one the computer's going to recognize best. My guess is it'll always recognize the slope intercept form. Okay, that's the end of the instruction on the chain rule. That's my favorite rule.